Hello, my name is Mr. Asprey and I've got another tricky question for you today. This one is super tricky, so much going on. I'm going to use loads of different stats techniques to solve it in what is going to be my final tricky question of the year. And just before we get into the solutions, I just want to quickly plug my live revision session that I did on Sunday. You can still pick up a recording of that and use the discount code TRICKY for 60% off, so it's only £10 now. And what you'll get is me for 3 hours. We go through two papers, of which there are 14 questions in each, so 28 questions. We get full written solutions, and also any questions we didn't complete in the session, you'll get video solutions for as well. Instant access, loads of 5-star reviews, loads of positive feedback. So yeah, check it out. Link in the description. Discount code TRICKY for 60% off, so it's only £10. And right, here we go. This is going to be my last video of the year, so best of luck in your exams. Let me know how they go, and let's get into the solutions. Okay, so it says the probability that Paul's train to work is late on any day is 0.15, independent of other days. The number of days on which Paul's train to work is late on a 450-day period is denoted by the random variable y. Find a value of a such that the probability that y is greater than a is approximately 1/6. Right, so I said I'm going to use a whole host of techniques in order to solve this question. I'm going to start off by writing that y is binomially distributed. There's 450 fixed trials and the probability of success is 0.15. We are looking for the probability that y is greater than some value a, and we want it to be approximately 1/6. So we can rewrite this because if in a discrete distribution, if you want to be greater than a, then that's the same as 1 minus being less than or equal to a. So a or less is the complement of more than a. We want that to be, closely to approximately 1/6. So we can rearrange this. So if 1 minus the probability of this is close to 1/6, then it means that that probability needs to be close to 5/5. Okay. Now, what we need really is an inverse binomial, which I don't have on this calculator. So instead, I'm going to approximate using the normal distribution, just for fun. So in order to do that, I need to work out the mean, which is NP, which will be the number of trials multiplied by the probability, which will be 67.5. And then to find the standard deviation, that's the square root of NP 1 minus P. So that is the square root of 67.5 times by 1 minus P will be 1 minus 0.15, so 0.85. Can't do that one off the top of my head, so I'm going to have to do that like so. Okay, yeah, fine. Let's just leave it as exact form, like that. Perfect. So that's the standard deviation. Okay, so that will then allow us to approximate this distribution. Let's call it W, normally distributed, with a mean of 67.5 and a standard deviation of 3 root 102 over 4, like so. Okay, and for the normal distribution, you write the standard deviation squared. In this slot here is the variance. Okay, so this is what we're trying to approximate, right? This. So if I want to approximate that binomial probability, then I will need to do the continuity correction when we use the normal to approximate the binomial. So being less than or equal to a would be the same as W being less than a plus 0.5. because remember, with the continuity correction, if we are a or less, then the highest value we possibly could be would be a plus 0.5, because that is the highest value which will round to a, and we want to be a or less, so that's the highest possible value, so it's a plus 0.5. Okay, so let's now try and work out what this value of a is. Let's just move that up there. And what we're going to do is we're going to draw a normal distribution for w. Okay, so for this distribution here, we are looking for this particular value, a plus 0.5, such that the probability to the left, because it's a less than, is equal to 5/6. We can have it exactly equal to 5/6 as well, because this is a normal distribution. So that area we can say is exactly 5/6 right there. Okay, great. Now, in order to work out what that a value is, we're going to have to use the standardized normal. So I'm going to draw another bell curve, like so. That's horrible. Let's do a better one. Yeah, that's better. We're going to go in exactly the same place. We're going to call that our z value. And we want the area to the left to be also 5/6, because these two distributions are proportional to one another. And this z distribution has mean 1 and standard deviation, mean 0, standard deviation 1. Okay, so what we can do is we can find this z value. We can find the z value which has an area of 5/6 to the left. So we can do that by going into distribution, inverse normal. We want area to be 5/6, and we want the standard deviation to be 1 and the mean 0, and we get a z value right there of 0.9674. And this is great, because now what we can do is we can convert between these two distributions using the formula. So let me just grab a little bit more space, like so. And we know that the formula that links these two distributions is that the z is equal to the x minus mu all over sigma. Okay, we know that the z value is equal to this, as we've worked out, and that's equal to the x value, which is this one here. So that is a plus 0.5 minus mu, which we said was 67.5, all over the standard deviation, which is 3 root 102 over 4. Lovely. Okay, so we can find the a value, which is going to give us an area of 5/6 to the left in this normal approximation of the binomial. Okay, so let's just go to our calculator here, and what we'll do is we'll do 0.9674. We'll multiply that by 3 root 102 over 4, and then we will add over the 67.5, and then we'll minus over the 0.5, and we will get a value for a of 74.3. Lovely. Okay, now I just want to double check to make sure, because of course a needs to be an integer, because it's a discrete binomial, but we have obviously converted to a normal, so we're allowed to have decimals in the normal, but we need an integer for the discrete binomial. So if I go into the calculator here, and I go to binomial CD, let's just check to see how good this normal distribution approximation is. Because I know, in fact, that some people will be saying, before you write it in the comments, that, hold on a minute, the probability isn't close to 0.5, and we need to have the probability close to 0.5 to approximate with the normal. Hello, this is me after recording and editing the video, and I've realised that I perhaps could have explained this point a little bit better, and that is that, yes, p being close to 0.5 is a fantastic way of ensuring that the binomial distribution that you are trying to approximate is symmetrical, and therefore the normal will be a great approximation for it. However, there is a better guideline, and which is not touched upon in the EDEXCEL spec, so you don't need to know this. But what it does mean is that in other specs, or maybe some MADAS questions, you are asked to approximate the binomial when p is not close to 0.5, and you can do that. It is allowed as long as n is sufficiently large enough. So in summary, all you need to know for EDEXCEL is that you can't use it when n is not large and when p is not close to 0.5. It'll be really clear when you have to use the approximation of the binomial. But this is just a bit of added knowledge in case you're interested as to why we can use it in other questions on different specs. Okay, so let x equal 74, let n equal 450. The probability was this. Okay, is that close? I don't know. Well, what we can do is we can store that in as A. And then maybe let's also try 75. We'll store that as B. And then we could do a little bit of change of sign actually to see which one is closer and to see if the value does actually lie in between the two. So 5, 6 minus A, which was the value we had for 74. Hopefully this gives us a very small number. It does. Okay, nice. And then what about if we do minus B? That's the value we had for 75, and that is larger, but there's a change of sign, which means the root does lie in between the two. And the one that was closest was A, which was when we chose A, little a, to be 74. So 74 is our answer to part I, and that is 3 marks. But yeah, that is a valid way of solving that question. It's the way that I chose to do it. Come at me in the comments if you think that that's a bad way of doing it, but I enjoyed it, and hopefully you learned a few things along the way. Okay, right, on to the next part. Okay, so for the next part, it says that in the expansion of 0.15 plus 0.85 to the power of 50, the terms involving a 0.15 to the r and the 0.15 to the r plus 1 are denoted by tr and tr plus 1, respectively. Show that this is equal to that. Okay, right, so if we are expanding this bracket out, then what we would do is we would use the binomial expansion. And we would start with 50 choose 0, and we would times that by, well, first, what actually is the binomial expansion? It's n choose r times by p to the r times by 1 minus p to the n minus r. That's the formula for the binomial expansion. So in this case, we would do 50 choose 0, and then we'd have 0.15 to the power of 0, and then we'd times it by 0.85 to the power of 50. And then the next term would be 50 choose 1, and we'd do 0.15 to the power 1, times by 0.85 to the power of 49, and so on, and so on, and so on. Now, for a general term in the sequence, so when we are taking the rth term, we would have 50 choose r times 0.15 to the r times by 0.85 to the 50 minus r. And then the next one after that would be 50 choose r plus 1 times 0.15 r plus 1 times 0.85 Now this will be 49 minus r. Now let's just double check that works, because what we know about when we do a binomial expansion is that the powers of p and 1 minus p always add up to the overall power. So 0 plus 50 is 50, 1 plus 49 is 50. Here we've got r plus 50 minus r gives us 50. And let's double check if this one works. So r and the minus r cancel. 1 plus 49 gives us 50. So yes, this does work. Okay, so that is good. Okay, so these are the two terms then. Okay, so if we want to have TR, which we, TR, remember, is this one. So this is there. So the whole term is TR. So let's write that as 50 choose R, like so, multiplied by 0.15 R times by 0.85 50 minus R, and then that is all over t to the r plus 1, which again, t to the r plus 1 is the term that involves that. So it's this one here. So we can just put that on the bottom, which will be 50 choose r plus 1 times 0.15 to the r plus 1 times by 0.85 to the 49 minus r. Okay, great. Now, what is this? What is 50 choose r? Well, that is the function n choose r, which has a formula of n factorial over r factorial n minus r factorial. That is in the formula book, and that is the Pascal's triangle coefficient. That is the formula for n choose r. Okay, so let's include these this formula for the choose function. So this will be 50 factorial over r factorial. N minus r is 50 minus r factorial. And then on the bottom, we've got 50 choose r plus 1. So that's 50 factorial over r plus 1 factorial. And if we then do n minus r plus 1, that will be 59 minus r factorial. On top, we're timesing by this, and we're timesing by this. And then on the bottom, we're timesing by this and this. Okay, now we can do some cancelling. So that can cancel with that. Here we've got 0.15 to the r, and on the bottom we've got 0.15 to the r plus 1. So we've got extra power on the bottom, so we can cancel out, and it'll just be left with a 0.15 on the bottom. And here, this power is one more than that power, so we can just cancel out. We're left with a 0.85 on the top. Okay, let's then do this divided by that, which gives us 17 over 3, I believe. So we're going to have 17 over 3. And then let's do some careful sort of fraction work here. Because if we have this like 1 over a, and then we're dividing it by 1 over b, then that's the same as having b over a. So I'm just going to take this thing here and put it on the top, and I'm going to take this thing here and put it on the bottom. So we'll have this on top, and we'll have that on the bottom. Like so. Okay, lovely. Now we're just going to have to do some clever factorial work. So r plus 1 factorial is the same as r plus 1 times by r factorial. Yeah, because r plus 1 factorial is just r plus 1 times every number before it. So it's the same as r plus 1 times the number before it factorial. We'll keep this one, 49 minus r factorial, keep that on the top. And then on the bottom, we'll have r factorial, and we'll also have this 50 minus r factorial, which again is the same as 50 minus r times by the number before it, which is 49 minus r factorial. Because once again, if you have a factorial, you can write it as, for example, a factorial, you can write it as a times by a minus 1 factorial. Okay, great. So we're going to get some more cancelling here, and this is going to go with that, this is going to go with that. So we are left with our final result of this being equal to 17 lots of r plus 1 over 3 lots of 50 minus r. Perfect. Okay, good job. Okay, on to the next part, which is part 3, I believe. This beast question. The number of days on which Paul's train to work is late during a 50-day period is modelled by the random variable x. So x is binomially distributed because it's a fixed number of days. And again, the probability of being late is 0.15. Find the values of r for which the probability of x is equal to r is less than or equal to the probability that x is equal to r plus 1. Okay, well let's just figure out what is the probability that x is equal to r. Well, from a binomial distribution like this, we know the formula for that. It's n choose r times by the probability p. Let's just write it like that. Probability p to the r multiplied by 1 minus p to the n minus r. That's the chance of having an exact value on a binomial. So for this binomial, it will be 50 choose r times the probability to the r times by 1 minus the probability to the 50 minus r. Now, we know what that is. That from our previous work is TR. That was, of course, the term of that expansion with the 0.15 to the r. Okay, so we know that the probability that x is equal to r is equal to TR. And we also know, by the same logic, that for this one, the probability that x is equal to r plus 1 will be TR plus 1. Like that. Perfect. So now we can actually work out what they've asked us for, which is they want this. The probability that x is equal to that. So in fact, this is the same as rearranging it like so, less than or equal to 1, which is TR over TR plus 1, which is less than or equal to 1. Okay, so we've got an expression for that, haven't we? Yes, part 2, we have an expression for that. Beautiful. Okay, so let's just write that out as 17r plus 1 over 3 50 minus r needs to be less than or equal to 1. Okay, let's solve this equation to get as such. So 20r needs to be less than or equal to 133. Okay, so let's just quickly do that. 133 divided by 20. And that gives us, okay, so the r needs to be less than or equal to 6.65. Now, of course, r is, or the variable is discrete, so r needs to be a whole number. So r is going to be 0, 1, 2, 3, 4, 5, or 6. Great, and those are the values of r for which that the probability that x is equal to r is less than or equal to the probability that x is equal to r plus 1. Okay, so for part B, it says, hence find the most likely number of days on which the train will be late during a 50-day period. So we have to use the previous part. We have to use this. Okay. Now, for all of these r values, this green inequality is true. So if I was to draw this on a probability distribution, let's start with r is 0. That's going to have some value. But what we know is that the probability that x is equal to 1, so the next one along, is at least as big, if not bigger, than the previous one. It's definitely not smaller. It can't be less than the previous one. So it's either exactly the same or it's bigger. And that's going to be the case for all of these values of r up until we get to 6. They're going to be at least as big as the previous one, if not bigger. So let's say we get to 6 here. Now when we get to 6, the probability that x is equal to 6 we know is less than or equal to the probability that x is equal to 7. For the last time, this inequality is going to hold true, which means that 7 is at least as big as 6, and 6 is at least as big as 5, and 5 is at least as big as 4. So 7 is going to be the biggest number, or it could be equal to 6, but it's going to be definitely at least the biggest number. Because then when we get to the probability that x is equal to 7, that is not in this set. So therefore we know that this inequality doesn't hold true, which means that it is in fact the negation of that. So the probability that x is equal to 7 is greater than the probability that x is equal to 8. So we're definitely going to be going downwards on this side, which means that 7 is the biggest it possibly could be in terms of probability. So we're going to say that 7 is going to be for sure the most likely number of days. It could be tied with 6, and it could be tied with 5 as well, but we know that 7 will have the most probability out of all of the possible values of r. Even if it's tied, we know that it's definitely going to be the highest probability. So 7 is the final answer. What a beast question. I really hope you enjoyed that. This is my last tricky question of the year. It's been really good fun trying to produce as much content as for you guys as possible. I hope it has been helpful. If it has, then do stay subscribed and let other people know about my channel so I can try and get as many subs and as far a reach as possible. Anyway, I wish you all the best for your exams and all the best of luck post-exams. Bye for now.